Hello everyone, welcome to first problem solving sessions for linear algebra course. Today's topics are fields, vector spaces, subspaces, sum of subspaces, direct sums and direct products. Let's go to the first question. First question is, let f be a field. Show that the set of rational functions f of x is a field. Now, first let's look at what is the operation in f of x. Now, we know that f of x is equal to quotients px over qx such that px and qx are inside of p of x. They are polynomials, and q of x is not equal to 0 polynomial. So, and the addition defined as p of x over q of x plus s of x over r of x is equal to, this is an addition on this field, is equal to p of x times r of x plus s of x times q of x over q of x times r of x. And multiplication on this field defined as p of x over q of x times s of x over r of x is equal to p of x times s of x over q of x times r of x. Now, showing that these operations are well defined, show that these operations are well defined. This is an exercise for you. Now, let's check the field axioms. First axiom is commutativity of first field axiom is commutativity of addition, which is a plus b is equal to b plus a for all a and b inside, in our case, f of x. Now let's take, this was the first field axiom. You need to take two elements inside of the fx. Let's first choose p of x over q of x and s of x over r of x inside of the fx. Now let's look at we choose these two elements arbitrary, and we need to show that commutativity is addition is commutative. So, from definition, we know that this addition is equal to p of x times r of x plus s of x times q of x over q of x times r of x. Now, for here, we know that addition is commutative over polynomials, and since it's the usual addition, s of x times q of x plus addition commutative over polynomials. we can change the space of this to p of x times r of x over q of x times r of x. Now we need multiplication is commutative over polynomials. So from here, since multiplication is commutative over polynomials, we can change these two. So we have q of x times s of x plus r of x times p of x over r of x times q of x. So this is equal to s of x over r of x plus p of x over q of x. Now we need to show that addition is associative. Now again, we will take any p of x over q of x, s of x over r of x, t of x over z of x inside of the rational functions, set of rational functions. Now we need to show that this is associative. Let's take p of x over q of x plus s of x over r of x plus t of x over z of x. Now this is equal to p of x over q of x plus s of x times z of x plus r of x times t of x over r of x times z of x. And this is equal to p of x times r of x times z of x plus q of x times s of x times z of x plus r of x times t of x over q of x times r of x times z of x. Now, we know that multiplication is associative over the field of polynomials. So we can distribute this p of x inside. So we have p of x times r of x times z of x plus, again, also distributive law holds over the field of field of polynomials. So we can distribute q of x inside here. So we will have q of x times s of x times z of x plus q of x times r of x times t of x over q of x times r of x times z of x. Then we will have okay. Now here we have z of x and here we have z of x, right? So we can take z of x common parentheses. So we will have q of x times r of x plus, here we will have q of x times s of x, q of x times s of x, take common parentheses z of x, plus, we can take this one as a parenthesis, we will have q of x times r of x times t of x over q of x times r of x times z of x. So this is equal to p of x times r of x plus q of x times s of x over q of x times r of x plus t of x over z of x is coming from the definition of addition. So this is equal to p of x over q of x plus s of x over r of x plus t of x over z of x. So we show that addition is associative. Now we need to show that there exists an element 0 such that for every element of the fields 0 plus that element is equal to that element again. So there exists 0 in f such that, let's say 0 fx, such that 0 plus a is equal to a for all a in f of x. Now let's define 0 of x as 0 or 1, right? So this is a rational function, right? So this is inside of the f of x. So we can say take any element inside f of x such that p of x over q of x in f of x. So 0 over 1 plus p of x over q of x is equal to 0 times q of x plus 1 times p of x over q of x. So this is equal to p of x over q of x. So there is a 0 element, so we show the axiom 3. Now we need to show that there exists an additive inverse. F4 for every a in f, we need to show that for every a in fx there exists a minus a in fx such that a plus minus a is equal to 0. So take any, again we will take any fx, sorry, px over qx over fx. So, and if we take minus px over qx, then px over qx plus minus p over qx is equal to p of x minus p of x over q of x, and this is equal to 0 over q of x, which is equal to 0 of fx. 0 of x, let's say. Let's say this one as 0 of fx. So this one is the additive inverse. So this completes the proof of axiom 4. I mean to show that axiom 5. Fifth axiom is commutativity of product. Now we need to take again any two elements inside of the set of rational functions. Let's say p of x over q of x times r of x over s of x. Now we need to find that this one is commutative. P of x over q of x times r of x over s of x is equal to p of x times r of x over q of x times s of x. Again, product is commutative over the polynomials, so we can commute this to r of x times p of x over s of x times q of x. So this is equal to r of x over s of x times p of x over q of x. So we show the fifth axiom. Now we have to show that associativity of product, which is a times b times c, is equal to a times b times c for all a, b, c in a set of rational functions. Now again I need to take any p of x over q of x, r of x over s of x, and let's say t of x over a of x. So let's look at the p of x over q of x times r of x over s of x plus t of x over a of x. And this is equal to, sorry, this is not the product, sorry, addition, this is the product. P of x over q of x is times r of x times t of x over s of x times a of x, and this is equal to p of x times r of x times t of x over q of x times a of x. And we know that polynomials are filled, so they are associative. So we can write this one as p of x times r of x times t of x, let's put parentheses in here, and q of x times, sorry, parentheses are not here. The associativity, because of the associativity, we have parenthesis p of x, r of x, close parenthesis t of x, q of x times s of x times a of x, and our parentheses here. So this shows, so this is equals p of x times r of x over q of x times s of x times t of x over a over x, and so this is equal to p over x over q over x times r over r of x over s of x times t of x over a of x. So we show that product is associative over the set of rational functions. Now, Field's axiom 7 is that we need to show that there exists one of fx such that 1 times a is equal to a for every a in fx. We need to show there exists an identity element of product. So let's define 1 of x as 1 over 1. Like this is rational number, but rational number, we can see this as a polynomial. Then let's take any p of x over q of x in the set of rational functions. So 1 over 1 times p of x times q of x is equal to 1 times p of x over 1 times q of x, and 1 times p of x is equal to p of x, and 1 times qx is equal to qx. So identity element of fx times any element is equal to that element. have only last two axioms. One is there exists for every a different than 0 function, 0 of fx, there exists a inverse in f of x such that a times a inverse is equal to 1. So take any p of x over q of x over the set of rational functions. So non-zero elements. Now we need to show that for this element we have an inverse. So also take p of x over q of x times q of x over p of x. This is inside the set of rational functions because px is not equal to 0 since px over qx is not equal to 0 of fx. So this is equal to p of x times q of x over q of x times p of x. So q of x and q of x are cancelled and p of x and p of x are cancelled. So we have 1 over 1, so this is equal to 1 of f of x. So a inverse is equal to q of x over p of x for all a is equal to p of x over q of x. So last thing we need to show that product is distributive over the addition. So this is equal to a times b plus c is equal to ab plus ac for every abc in f of x. Now again we need to take any p of x over q of x, r of x over s of x, t of x over a of x in the set of rational functions. Now let's look at the p of x over q of x times r of x over s of x plus t of x over a of x. And this is equal to p of x times q of x times r of x times a of x plus t of x times s of x over s of x times a of x. So this is equal to p of x times r of x plus a of x, t of x times s of x over q of x times s of x times a of x. Now, since polynomials are fields, we can distribute p of x inside. So we will have p of x times r of x times a of x plus p of x times t of x times s of x over q of x times s of x times a of x. So we can separate this term inside of the two terms from here. So we will have p of x times r of x times a of x over q of x times s of x times a of x plus P of x times T of x times S of x over Q of x times S of x times A of x. Now again here we have A of x in denominator and we have ax in denominator. Also we have S of x in the denominator and S of x in the denominator. So we will have P of x over Q of x times R of x over S of x plus P of x times over Q of x times T of x over A of x. So we show that multiplication distributive over the addition. So we show that 8th field axiom is holds. So set of rational functions is a field. And this completes the question. Second question is show that if map fk to L is a field extension, then can't L have the same characteristic. Okay, let's remind what is the field extension. The injection K to L is called field extension. So this map is an injection. And what was the characteristic? Characteristic of a field is smallest positive integer and such that characteristic of a field f such that 1f plus 1f n times is equal to 0. And if there isn't any such n, we say that f is a field of characteristic 0. Okay. The injection of fields is called field extension, and characteristic of a field f is the smallest positive integer and such that adding n times 1 together is equal to 0. And if there isn't any such n, we say that f is a field of characteristic 0. Now we need to show that if f of k is field, then can't n have the same characteristic. First thing I want to show that, we have f k times l, and this map is 1 to 1 since it's an injection. Now first thing I want to show that, claim f of 1 of k is equal to 1 of l, and let's take any a in k. F of a is equal to f of a times 1k, right? Since 1k is the identity element of k, so this is equal to f of a times f of 1k. Since this map is an field morphism, I didn't say it before, sorry. This is an field homomorphism. So this is equal to okay. Now we have f of a times 1k, right? And both is in L and L is field, so we can cancel this f of a's. So we have 1L is equal to f of 1k. So this completes the proof of our claim. I will show this one case by case. Let's assume that case 1, characteristic of k and characteristic of L is not equal to 0, and say characteristic k is equal to n and characteristic of L is equal to m. So we will have 1k plus 1k is equal to 0 n times 1L plus 1L m times is equal to 0. Now let's look at the n is less than equal to first case I will look at first side I will look at m is less than equal to n. Let's look at f of 1k plus 1k. There is n times 1k's. So this is equal to f of 1k plus f of 1k, right? Since this map is an field homomorphism. So from here we prove that 1L is equal to f of 1k. So this is equal to 1L. Everything is equal to 1L. So we have addition of 1L's m times. But we know that, like from the definition of the characteristic of a field, characteristic is the smallest positive integer such that this holds. So m times this one also holds, right? Sorry. We have n times here. Also we have n times, so this is n times. So m is the smallest such integer, but n is also holding this equation. So we can say that m is less than equal to n, right? Since m is the smallest such integer. Other side, now we show that n is less than equal to m, right? So 0 is equal to m times 1L, right? So this is equal to 1L, every 1L is equal to f of 1k, right? And these are m times, so this is also m times. So this gives us, and these are, since this is f inside field homomorphism, we can take this one inside of the f. So we will have f of 1k plus 1k plus 1k. So this is m times. And since this map is an injection, let's start with the new page. This map is injection, right? If an element is equal to 0, then that element is equal to 0. So we will have 1k plus 1k. This is again m times is equal to 0. But from the definition we know that n is the smallest such integer. So n is less than equal to m, since m is the smallest one. Now we show that for case 2, if characteristic k and characteristic L is non-zero integers, then they must be equal. Now let's assume that case 2 characteristic k is equal to 0 and characteristic L is equal to n not equal to 0. Then we will have that 1L plus 1L is equal to 0, right? So we know that this from here we can say that 1K is equal to 0. These are same as other case. Fill this gap and this is equal to so this gives us contradiction since we say that is equal to 0. So case 2 is not possible. Case 3 is exercise for you. You will see that case 3 is also not possible. So there is only one case. This case is the case where characteristic k and the characteristic L is equal to 0. So this is okay. Okay. So characteristic k is equal to characteristic L, whether characteristic is 0 or non-zero integer. So this completes this question. Third question is, let the map f k to L be a field extension. Show that L is a vector space over k. Addition is the field addition over L. So we want first, second, third, and fourth axioms are satisfied. Since L is a field. Now we also need to define a scalar product. Now we have, we need to take C in K and V in L, right? Take any. And we need to define this scalar multiplication as f of C times V. This is f of C inside of L and this is inside of L, so this multiplication inside of L. This is the field product inside of L. Since L is a L, there exists a product, right? So this is that product. So we need to show that there exists a multiplicative identity element. Okay, after defining the scalar product, we need to show that identity element of k, multiplicative identity of k, satisfies 1 times k times v. This is the vector space operation, is equal to v for every v in L. Now, 1 of k times L of v is equal to f of 1k times v, right? And we know that from the previous question, we know that f of 1k is equal to 1L. This is the 1L times v, and this is the v. Please remember that dot of L is the product, vector space product, and this dot is the field product. Product of a field. And this was the fifth vector space axiom. Now we need to show that sixth vector space axiom, which is if you take a plus b inside of k and v inside of the L, a plus b times L is equal to a times v plus B times B. I'm going to show this one. Now we have take any AB inside of the K and V inside of the L. Okay, A plus B. This is the addition under K times vector space product times V is equal to f of A plus B times V. So, since this is an field homomorphism, we can separate this f. We have f of A plus f of B times V. So we can distribute this one inside. We will have f of A times V plus f of B times V. So we will have A times V plus B times V. So sixth axiom also satisfied. I mean, show that seventh axiom, which is A times V plus W is equal to AV plus WV. So this is this one, this is this operation, and this is this operation for every A inside of K and V and W inside of L. Now let's look at take any A inside of K and V and W inside of L. So A dot V plus W is equal to A dot L, f of A times V plus W, right? And L is a field, so product, we can distribute product. So we will have f of A times V plus f of A times W. So this is equal to A dot V plus A dot W. So seventh axiom is satisfied. Now we need to show that the last axiom, which is A times B times V is equal to A times B times V for every AB inside of K and V inside of L. Again, these are the vector products we defined before. Now, A times B, this is the product inside of K, and this is the vector space product inside of L. This is equal to f of A times B times L. Sorry, there is no L right now. This is the vectors field product. So we will have, again, this f is a field homomorphism. So we can write this f as f of A times f of B times V. So again, since L is a field, product is associative, so we will have f of A times f of B times V. So this is equal to f of A times B dot V, and this is equal to A dot B dot. So therefore, L is a vector space over K. So this completes the proof that field L is a vector space over K. Fourth question. question is show that if F is an infinite field and V is a vector space over F contains a non-zero vector, then V must also be infinite. Now, from the question, we know that V contains a non-zero vector. Take V. Let's take this non-zero vector over V. And now I want to define define a map define map I such that this map is from F to B, such that if we take any elements from F, we will send this one to x time scalar multiplication x times V. So we will send this every x inside of S to x times V. So now I want to show that this map is injective. So let's take any x and y inside of the F, right? And assume that Ix is equal to Iy. Then this implies that x dot v is equal to y dot v. So this implies that if we take this one, the other side, v minus y dot v is equal to 0, right? So since this is a vector space, we can take this one as the v common parenthesis, parenthesis x minus y dot w is equal to 0. So since v is not 0, this means that x minus y is equal to 0. So x equal to y, right? So this implies that so I is 1 to 1. So from here you can deduce that number of points inside of F less than equal to number of points inside of V. So since this is infinite, V is infinite. Question 5 is coming from last year midterm. Let V be a vector space over a field F and W is under V. Write the definition of W to be a subspace of V. Then using your definition, show that if V is the functions from R to R as a vector space over R and W is a subset of odd functions, then V is a subspace of V. Now let's write the definition of subspace. W is a subspace of V if subspace 1, axiom subspace 1, 0 vector times V, 0 vector of V is in the W, 0 vector must in W, and if we take U and V inside of W, then U plus W must be inside of W, and if U is in W and C is in F, then C times U is in W. Now RV is the functions from real numbers to real numbers, and RW was the odd functions of real numbers. Odd function means that f of minus x is equal to minus f of x for every x in R, right? Now we need to show that for the first axiom, we need to show that 0 inside of the x. Now 0 of x, 0 function is 0 of x is equal to 0 for every x in R. The function sending every x to 0 is the 0 vector of R vector space. Now we need to show that this is an odd function. Now 0 of minus x is equal to 0 and minus 0 of x again is 0, right? This sends everything to 0. So 0 of x inside W. Now we need to show that second axiom. Let's take any f and g inside V. So f of minus x is equal to minus f of x, and g of minus x is equal to minus g of x for every x in R. Now we need to show that f plus g of minus x is equal to minus f plus g of x. Now this is equal to f of minus x plus g of minus x. So this is equal to, since f and g odd, we have this one is equal to minus f of x and this one is equal to minus g of x. And if we take the common parenthesis, we will have f of x plus g of x. So f plus g is an odd function. So f plus g is in W. Now we need to show that the third axiom, which was if we take u and v and c and f, c times u is equal to W. Now take c. Our f is any field. Let's take any c inside of f and f inside of the W. Therefore, f of minus x is equal to minus f of x. So let's look at the c times f, the function c times of f minus x. So this is equal to c times f of minus x. So this is equal to c times, so this one is equal to minus f of x. So this is equal to, we can take minus outside, c times f of x. So c times f is an odd function. So this completes the proof. 6 is decide whether or not following sets W are subspaces of the given vector space V. And the first one is field is the real numbers, vector space is the functions from R to R, and let A be the subset of R, and W is the functions inside of V such that absolute value of fx less than or equal to 1 for every x inside of A. And the answer is no. Okay. Now let's show this why it is not true. Choose A is equal to open interval 0 to 1. Okay. And fx as the identity map is equal to x for every x in W, right? Now, first we need to show that fx is inside of the w. Now, absolute value of fx is equal to absolute value of x, right? And our x's between 0 and 1, and they are not equal to 0 and 1. So this is less than 1. Or let's say, we can also take this one as a closed interval. Let's take a as a closed interval 0 to 1. Then absolute value of x less than equal to 1. So fx is in w. And define a. And let's take 2 inside of the f, right? Like 2 is inside of the r, like our field in that. Let's look at the fields, scalar multiplication. 2 times fx is equal to 2x, right? And let's look at the absolute value of 2x. Absolute value of 2x is equal to 2 times x. But if we choose x is equal to 1, this is equal to 2 times, let's write here, if we choose x is equal to 1, absolute value of 2 times f of 1 will be equal to 2 times 1, absolute value 2, and which is greater than 1, right? So 2 times f x, not an element of w. So w is not an subspace. So w does not satisfy axiom 3, so w is not a subspace. Part B is, again, field is real numbers and V is the functions from R to R, and let's A be a subset of R and W is the functions of V such that f of x is equal to 0 for every x in A. Now, first thing we need to show that 0 vector is in W. So, in our case, 0 vector is a 0 function, and 0 function is equal to 0 for every x of V, and since A is under V, so that 0 of x is equal to 0 for every x in A. So, first part was easy. Now the second part, we need to show that for every f and g in W, we will have f plus g is in W. Now let's say take any fx and g of x in W, so that f of x is equal to 0 and g of x is equal to 0 for every x in A, right? Now let's look at the f plus g of x, and this is equal to f of x plus g of x, right? And over A, this is equal to 0, right? This is equal to 0, so this is equal to 0 for every x in A. So f plus g is in W. So second property of subspace are satisfied. Now we will take f in W and c in f. In our case, it's R. Let's say R. Then c times f is in W. Again, take any f in W and c in R. Therefore, fx is equal to 0 for every x in A, since fx is in W. Then c times f of x is equal to c times f of x, right? So since this is equal to 0 for every x in A, this is equal to 0 for every x in A. Therefore, B is a subspace of V. So this completes the question 6. Question 7 is, say V is a vector space and W1 and W2 two subspaces. Show that W1 union W2 is a subspace of V if and only if one of the Wi's is subset of other. Now we need to show that this if and only if statements. Let's prove this side, which is if one of the Vi's is a subset of other, then V1 union V2 is a subspace. Now I will prove this side without loss of generality. Say W1 is subset of W2. And this implies that W1 union W2 is equal to W2, right? Since W1 is subset of W2, so union is equal to W2. So since W2 is a subspace, so W1 union W2 is a subspace. This case was the easy. Let's look at the other case. For the other side, let's assume the contrary. Assume that neither contains the other. First, suppose that V1 union V2 is a subspace. Then assume that neither contains other. So we can find W1 inside of W2 such that this small W1 is not in the W2, and also W2 inside of W2 such that W2 is not in the W1. Now W1 plus W2 is in W1 plus W2, right? Okay, before coming here, I want to show this one step by step. Now, V1 is in W1, right? Let's say W1 is in W1 and W1 is under W1 union W2. So, small W1 is in the W1 union W2. Same is true for the small W2 is in, sorry, this is under W2. So, since first assumption is W1 union W2 is subspace. So, W1, since both of the elements are in the union, W1 plus W2 is in the union. So, since W1, because W1 union W2 is subspace, now W1 plus W2 is in the W2, right? So from here we can say that W1 W2 is in W1 or is in W2, right? If something is in the union, it must be inside one of them. Now, without loss of generality, let's W1 plus W2 is in W1. So let's look at W2. W2 is equal to W1 plus W2 minus W1, right? And now we know that this one is in W1, right? And this one again is in W1. So since W1 is a subspace, W1 plus W2 minus W1 must be inside W1. So, but we choose W2 as not in W1. So this gives us contradiction. So one of the VI's is subset of other. So this completes this side of the proof. So both of sides show that this statement is true. Question is again the midterm 1 question of last year. And the question is, decide whether the following statement is true or false. In each case, justify your answer. And the statement is, let V be a vector space and K, L, N, and M subspaces, then K plus L intersection M is equal to K intersection M plus L intersection M. And this statement is false. I will show this with a counterexample. Let's our F is R and our field is R square. This is the tuples X and Y such that X and Y is in R. And let's take K as X zeros such that X in R, and let's take L as 0, X in R, and that takes M, X and X in R. And these three of them are like subspaces of R square. Now we need to show that this one does not satisfy. Let's look at. Now K plus L. Let's look at the K plus L. In K we have x0, x in R. They are arbitrary x's. And L is equal to, let's say, not x0 of y is in R. Okay. Now K plus L is equal to hold x and y such that x and y in R. So this is equal to V, right? So K plus L intersection M is equal to V intersection M, which is equal to M, right? Since M is subspace of V, then V intersection M is equal to M. Now we also need to find what is this one. K intersection M plus L intersection M. Now K intersection M, let's look at the K intersection M. K is tuples x and 0, x in R, and M is the x and x in R. Like both of the components must be equal, right? And we know that second component always 0 in K, so first component must be equal to also 0. So K intersection M only contains 0 plus 0 of V there. Let's say it's 0 of V. Let's look at L intersection V. Again, L is the tuples 0 and y is in R, and M is x and x in R. So again, second component and first component must be equal, and we know that first component is 0. So this means that second component also must be 0. So this gives us only the 0 vector. So this again 0 vector. So 0 vector plus 0 vector is 0. So but m is not equal to 0 vector, so they are not equal. So this shows that statement is false. This was the end of this problem solving session. Thank you for listening to me, and have a nice quizzes. See you next time. Bye.